Hi everyone, and welcome to a new video about LC ladder filter design. This is our example number 3. In this example we'll look at the high-pass filter having an elliptic response characteristics. Of course we'll work out our calculations step by step and also verify these in SPICE simulations. So the objective is design an elliptic response LC ladder high-pass filter. And I must have a 50 ohm double terminated shunt input circuit, and we will see this shortly what it means. This is the circuit we need to design our filter, and these are the normalized source and the load resistors, each 1 ohm. The specifications are shown here. The maximum passband ripple must be 0.2803 dB, and again our rho is 25%, which is our reflection coefficient. We have the minimum stop-band attenuation of 20 dB, the passband frequency must be 1.6 MHz, and the stop-band frequency is 1 MHz. Okay, let's look at our solutions. Step 1 is always calculate the filter order from the specifications and then also use a table for the required minimum stop-band attenuation. Now for the transition sharpness, required transition sharpness, we'll look at the ratio of this passband and the stop-band frequency. That's shown here. In this case we have 1.6 MHz over 1 MHz. That is just 1.6. Now looking at a table of the elliptic response, filter order of 3, we see here the normalized values for the different ripple values. So 0.0988 dB and 0.2803 dB what we actually have, and also the other ripple. Now we see here the following in the table. In this case we see in the column here at looking at the, let's say, the omega r, which is our transition sharpness, that we have here 1.6243, which is larger than the maximum allowed 1.6 of the required sharpness for the transition. And if you go down, then this is a possible candidate, but it also depends on the a minimum which you have here, and that is actually shown here. So you need to check two columns, one for the a minimum and one for the omega r. Now looking at this, we have actually here the candidates which are here, because then the minimum is also above this 20 dB. This is also fine because it's also above 20 dB, but this is not fine. Why? Because this 19.88 is less than 20 dB. So it is good in terms of the transition sharpness, but not in terms of stop-band attenuation. If we go up, it will be even better as in terms of stop-band attenuation, but then the sharpness will go up. So that is not what we wanted. So we need to look at these two specifications together. So looking at the specification, we require a third order filter and is 3. Now to satisfy the requirements of both maximum of 1.6 for our transition sharpness and a minimum stop-band attenuation of 20 dB, we can choose between rho 18 and 19. And it really depends on the specification of accuracy or the available components. So, and also we have an option to go for a low-pass filter prototype with minimum inductor or low-pass filter prototype with minimum capacitor. So these are different circuits having the same characteristics and same response in the frequency. So then we have these two rows for our minimum inductor count and minimum inductor capacitor. We have these two rows. So we can design the filter as said using two formats or two arrangements. So one is the minimum inductor and the other one is minimum capacitor. That means we have few inductors here and few capacitors in this case. And again, the design result will be exact same. This is just the choice depends on the available components and also the required accuracy. So we'll select in this case from these tables the second row each. So we will also look at the circuit for both types, so both arrangements. Okay, taking them here together and looking now at the circuit for the minimum inductor prototype low pass filter. You see here there is only one inductor, so it is just minimum inductor. And this is now minimum capacitor because the count here in the inductor is 3 and we have only 1 capacitor. You see that this circuit is different than this circuit. This is also called the pi circuit and this is the T circuit. You see here the capacitor here, the capacitor there, but there's an inductor here, inductor in series, and then there's a shunt here of a series combination of inductor and capacitor. Here you have a parallel, so there's actually always a complementary version of it. So we can now calculate from these values the scaled values what we want at the end. So step 2 is calculate or define your frequency scaling factor Kf, which is just omega p, which is then 2 pi times fp. So 2 pi times fp will be then 2 pi times this 1.6 megahertz, so that will be 3.2 pi times 10 to the power 6, or just 1.6 megahertz. Now step 3 is the calculation of the scaled component values. We start with the high pass filter circuit with minimum capacitor count. Why high pass filter? Because we need to design a high pass filter, but we start with a low pass filter prototype circuit and we convert that to a high pass filter. That means this conversion here is as follows. We have also discussed this in the previous videos about Butterworth response, Chebyshev, and also Bessel responses. So we need to transform the capacitors in inductors and inductor in the capacitors, and see also the parameter. That means it must be also scaled up to get this specific frequencies. We will also do that shortly for the other variation. And now you see actually this circuit, which was in the low pass prototype format of minimum inductor, is now minimum capacitor. That's also what we have here, so that is now complementary. So these are the formulas for calculating the L1 prime. You see the Km, which is 50. Why? Because we need to go from RS of 1 ohm to 50 ohm as required. The Kf is from step 2, and C1 here is 1.1061. That's just from the table. Now you get this value. In a similar form for L2 prime here, you now look at the C2, and that is also from this table. And you get now this value. Now the C2 prime here, which is related to the L2 value, which is shown here, and now we get this value. And the final one is the L3 prime, which is exact same as L1 prime. Now we have this value. You also need to scale up this RS and RL prime, where they are just 50 times 1, so 50 ohm each. Now we have all the components for this circuit for our final design. So we can now look at the designed circuit in the simulator. This is now the circuit in the simulator. You see here the prototype low pass filter, normalized, and here the high pass filter configuration, and it is now scaled up to the required frequency and other parameters. Okay, now you see again here the inductors and 1 capacitor, as we have also here, and the values of the components are also shown here. Let's also look at the other variation, which is then the low pass filter prototype with minimum capacitor count, which means again here, which means that the high pass filter will be then with the minimum inductor count. So we can now transform this into this. Well, you see again the RS will be RS prime, also the RL will be RL prime. Now the inductors will be transformed into capacitors. C1 prime, C3 prime, L2 will be C2 prime, and this will be an inductor. So there's only one inductor here. Now the formulas are shown here. This is C1 prime. You see here again the Km and the Kf, the same values. And now we have again this coefficient, which is the exact same here, where now it is for L1 and L3 as the normalized values. This is now what you get, almost 1.8 nanofarads. C2 prime in a similar form. Now you get this coefficient as L2 prime from here. And a C3 prime is in this case exact same as C1 prime, and then again the RS prime and RL prime, they are again 50 ohm each because the Km is 50. Okay, now the design circuit then will be this. You see again here the prototype low pass filter, this T configuration. Now you see also the capacitors C1, C2, C3 and L2, and also the RS and L scaled up to 50 ohms. Okay, now let's look at the simulation results for each filter circuit arrangement First we start with a high-pass filter circuit with minimum capacitor count. This is the body plot. You see here the gain and some values and labels we need to discuss. First one is the high frequency gain, which is 0.5. It's a scalar, and now in dBs you can convert that using 20 log of that 0.5 will be then minus 6.02 dB. So that is as expected. Looking at 1.6 megahertz here, you see that the ripple from the baseline going down to this value is 0.2806 dB, which is a little bit larger than the maximum allowed ripple, but that is not really that much. You can actually consider this as a rounding of error, so this is also perfectly fine. The following label is about the stop band attenuation. Looking at 1 megahertz, you have this gain, and again, looking from baseline, you go down by 22.02 dB approximately, or 22.01 dB, and that is at least 20 dB, so that is also according to specifications. And you also have this cutoff frequency here of 1.37 approximately megahertz. So we can say the specifications are met in this case, and we also see that we have only one notch. That means we have a third order filter. Okay, explanation results now for the high pass filter circuit, but now for minimum inductor count. And this is now the body plot for that. And now you see this circuit where you have the body plot here. Again, we go through the labels. Again, the same high frequency gain of minus 6.02 dB as discussed before. At 1.6 megahertz, I see here a ripple, or the reduction in the gain of 0.28 dB, which is less than what maximum allowed, so this is fine. You see also the stop band attenuation here, and now we go down by almost 21.996 dB or 22 dB. Again, at least 20 achieved, so that is also perfectly fine. And we also have the cutoff frequency of 1.37 megahertz, which is close to what we have before for our other arrangement. And now see actually these three labels prove that we have achieved or met our specifications. So we can say the design is completed. So we have seen now two different arrangements for our high pass filter configuration for this specific example. If you have any questions, comments about this example, please tell me and I will try to answer them as soon as possible. See you next time in another video. Take care.